So we spent a lot of time talking about references, which are, ways to have different names refer to the same variable. And we've also talked a lot about pointers, which is another type of variable, but where the value of that variable is an address of some other variable. And they synergize very well with functions, because when you use a function, you're having to refer to a name or a variable that you pass into that function. And you could say if that reference should be a reference like with using the same name, like the same variable underlined, or it should be a pointer to a particular value, meaning that you're passing in really the address of a variable, or if you just want to pass a copy of the variable into the function, which is actually what pretty much all the functions you've written so far have done. So when we're talking about what we do when we define a function, by default, you copy an argument into a parameter, because once again, you have the invocation of the function. When you call that function, you provide a couple arguments. Those arguments are copied into the parameters of the function, which is what the function actually does with those values. And that's what happens by default. And most of the time, that's fine. However, you can actually specify the type of a parameter to be a reference. You can say, I don't want just string x in my parameter list. I want a reference to a string named x. And then what happens there is, instead of copying the argument to the parameter, what you'll get is that function will now get a reference to the argument. And why does that matter? Because it means that that function, if it changes that parameter, it also changes the argument. So it allows functions to change variables that exist outside of the function. All right. So here's an example of defining a function, specifically the swap function, which you've seen before, that uses references instead of just copies. So note, this swap takes two longs, but not just any longs. It takes two references to longs. You see the ampersand right there? Now, what this says is that when I call this function with, two different variables, when I change first and I change second in here, it will change the actual arguments in the function that's calling, in the part of the code that's calling this function. Because if I got rid of these ampersands, I just had this exact same code without the ampersands, what would happen here is I would make a new long called temp. It'd get a copy of the value first. I would set first to be equal to second, set second to be equal to the temp. And then this function would have basically no effect on the outside world, because first and second would be just copies of variables. You're making these changes to copies of variables that get removed when the function is done running. But by making these two parameters references, it means that when I say first is equal to second here, I'm actually changing the argument that was passed into this function. Now, this is one way to write the swap function. Now note, swap doesn't have to return anything, because its whole job is to change its two parameters. Is more specifically the arguments that the parameters are references to. You can also do the same thing with pointers. Note here I have a pointer to a long name first, and I have a pointer to a long name second. Now, how would you do a swap with pointers? Well, once again, what we do here, if we make a new variable called temp, which is equal to the dereferenced first, meaning the value that is pointed at by first. And then we say that the value pointed at by first is equal to the value pointed at by second. So we're copying whatever is stored in the thing pointed at by second. We're sticking that in the thing pointed at by first. And here we're saying the thing pointed at by second gets the value of the temp, which is, the old value that was pointed at by first. Both of these achieve much the same effect of changing their arguments that this function was called by. And so once again, just to say this in text form, another way to change your arguments is to use pointers, is to say, hey, I want to be able to use pointers to dereference those pointers to get at variables that exist outside of my function. And so through those pointers, you can change the arguments. The other thing we can do is we can actually add const into this thing as well, to basically say how we want to let our functions change our references and pointers. So, multiple choice question time. Here is a given function definition. the function returns an int, it's named func, and it has 3 different arguments, a, b, and c. I want to know which of those parameters copy their argument. Alright, so let's start with a here. Notice that this is just, a is just a string. It's not a reference to a string, it's not a pointer to a string, it's just a string. And so what that means is that you're just using the default behavior, which is making a copy. So whatever argument is passed into the first position of this function, it's going to get copied. So if you have a huge text, string, that's going to get copied into this function, which might be an expensive operation. It might not be. It depends on how big a is. All right, what about the second one? Here we have a pointer to a string. Okay, well, what's getting copied here? Well, in order for me to call this function, if I need to give it a pointer, I'm giving it basically an address. And now technically, if you wanted to be confusing, technically that address, the pointer itself, is copied. You're copying that address. What you're not copying is the thing being pointed at, though. So often, pointers are very small. They're just an address. So copying a pointer really doesn't cost really much of anything. The string being pointed at could be huge, but that is not being copied. All you're copying is an address. So technically, B does copy their argument because the argument is an address. But in reality, it's not copying the thing being pointed at, which is often the thing you're trying to avoid the copy with. So technically, B is copied, but it's not a copy that is meaningful because it's tiny. What about this one? C. C is a reference to a string. All right. Is that copied? No, references are never copies. References just say C is now a new name for an existing variable, specifically an existing string. So there's no copies necessary here. So which of the following parameters copy their arguments? A, definitely the string is getting copied. B, technically the pointer is getting copied, but there's no strings being copied in B. And in C, there's no copies happening whatsoever. All right. So what happens when you invoke a function? So here is a function that has 2 arguments. And what happens here is each of these arguments are then paired with parameters in a given function definition. Note this function doesn't return anything, so you're not allowed to return something from this function. It's named, would go in here. So this function is named function. And now note, param1 is a reference to an int, and param2 is a reference to a long, which means that there are no copies being made here. It just means that whenever I say param1, it's just the same thing as if my code had said arg1. And whenever I say param2, it is just the same as if I had said arg2. These things are referring to the exact same things. Param1 has the same address and same value as arg1, just like how all references work. So here is an example call where we're calling the version of swap that uses references. Note here I have 2 longs, one called 1 and 2 called 2, and I just say swap 1 and 2. After calling this, the variable 1 will have the value 200, and the variable named 2 will have the value 100, because when I'm calling swap with references, it's allowed to change these arguments. Now note, because they're references, I don't have to put any special notation to denote that, hey, this one is going to get referenced. The compiler handles that all very nicely. Now here is a version of main that I'm calling the version of swap with pointers. Note, I still have the same 2 variables here, a long called 1 and a long called 2. But here I have to put the ampersand in front of the 1 because 1 is not a pointer, is it? 1 is a long, and this version of swap requires pointers, and so I need to give it the address of 1, and I need to give it the address of 2. So, to be honest, most of the time when you're going to be providing arguments to functions, you probably want to either have them be making copies because you want, that function to be working with a new version of it, or you want to have it be a reference so that that function has the ability to change that argument. So sometimes you want functions to be able to change their arguments. Now, there are times when you don't want a copy and you don't want the ability for a function to change its arguments, because changing a function that changes its arguments is often confusing and unnecessary. So what you can do is you can make the function parameter be a constant reference. And of course, you guys have played around with constant references before now. A constant reference is a reference, meaning it doesn't make a copy, but it's const, meaning that reference isn't allowed to change the original variable. And so if you want to make a function parameter that avoids copies, but is also not allowed to change that argument, you should use a constant reference. And so here, let's show you an example of that. Okay, so here is a function. Here is a main function. We'll look at the main function first, where I'm making a double called r for the radius, and I'm making a constant double called pi. And unfortunately in C++, there's not like a nice pi constant. And so you can calculate the pi constant by using the arctangent of 1 times 4. This gives you 3.14. I could have just wrote pi is equal to 3.14 here if I wanted to, but this has a lot more digits than just those 3. And then I see out, give me a radius. I read in an input into r. I have a really high precision count here. And then I say that a circle of a given radius has an area of, and here I call this particular function. Now, if I look at this particular function, this circle area function, what does it do? Its job is to return the area of a circle that has a given radius and this value for pi. Now, does calculating the area, should that change the radius of a circle or change pi? No, it doesn't make any sense. So what we could do is we could just say that circle area is going to be just make a copy of the radius and make a copy of pi. And now we know, because we're making copies here, that even if this function tried to change radius in any way, it wouldn't affect r and pi out here because these would just be copies. Now, copying doubles really doesn't take any time at all. This isn't an example where it's really necessary to use references to avoid copies. But, you know, if for some reason copying doubles was more expensive, or if these arguments were bigger, here, by putting in references here, I'm saying, hey, don't make copies of r, don't make copies of pi, just let me use them as is. Now, if I allowed for this function to change radius, which it's not really necessary here, but this is legal code. What this would do is it would make radius go up by 2. And what that would mean is that this r, which was originally, I don't know, like a 13, whatever somebody typed into the console, if I tried printing the r after calling circle area, r would now be 15. That's probably not what I want to allow to happen. I don't want my radius to be made bigger. So what I could do is I could say, I'm going to promise, my function promises that it will not change radius or pi even though they're references. And now if I tried to compile this code, I'd get a compile error because it'd be saying, hey, radius is a constant reference. You're not allowed to change radius, which is why I had the line commented out so that this code does compile.